Okay, this is our mock question 6, okay, all about conduction. Now, in this first question, we're being asked about the mechanisms of energy transfer that make metals good thermal conductors. Good thermal conductors are actually the same here as good electrical conductors. Okay, now a big issue that students have with this is that they just tend to tell us sort of properties of metals, and actually it ends up being quite a kind of chemistry style answer that we get. We're more interested in the processes of energy transfer within the metals themselves. Okay, and there are two ways in which metals will transfer energy through conduction. The first one is the fact that particles are close together, okay, and therefore they can pass the energy via vibrations. Okay, actually this is the same energy mechanism, transfer mechanism as in insulators. Okay, it just happens to not be particularly fast. Okay, excuse the notifications there that I'm getting through my computer. All right. What makes metals fast is to do with their structure. Okay, you should be aware that metals have delocalized electrons, a positive ion and a negative electron, and it's the electron that's carrying the energy. They can travel freely from one end into the other and therefore transfer energy. So it's really this idea of delocalized electrons. Now, often I'll get, for example, this written down, delocalized electrons. I tend to give credit for this. However, I would warn against that. I would suggest that you need to write a sentence which explains why the delocalized electrons help with the energy transfer, not simply the fact that there are delocalized electrons. Okay, I understand what you mean when you write this. However, I think it's really important to communicate to the examiner exactly what you know and how that aids the conduction process. Okay, we're then asked to think about the surface color of an object. Now, there's a big red flag here. Okay, as soon as you see anything to do with black and white surfaces, then we are thinking here about radiation. We are not thinking about conduction. Our answers in the following sections are not to do with conduction. Okay, we're thinking about radiation because radiation is all to do with color. We know that black surfaces will emit and absorb energy radiation, and white surfaces, silvered surfaces, will do the opposite. We've got a graph which shows the temperature of these two cans, P and Q. Okay, and we're being asked in the following question to determine which one's which. You can see here clearly Q has got lower change in temperature over the same time. Okay, lower rate of change, and then you can see here that P has a really quick rate of change. Therefore, P is the black one. And Q, I've written here shiny, this should say white, my apologies, okay? The black one is losing the energy at a greater rate, okay? So in the question, it says here, well, first it asks us to state the room temperature. This is actually one that really some students really struggle with. The room temperature is simply the temperature that the cans are approaching. You see that they're leveling off to this nice 20-degree mark, okay? And that is the temperature of the room. Why? Well, because when our cans have reached the same temperature as the room, they will neither cool down nor heat up. This is called being in thermal equilibrium, and it basically means that the temperatures of the two things are the same. So the temperatures of the cans will be 20 degrees. Now often, some students might write 80, and that is a scary answer because it implies we haven't really read the question. Okay, 80 degrees here, but the temperature of a room is unrealistic. So just be careful when you're checking your answers. 20 degrees, we're expecting an answer like that. Sometimes when we do calculations or we state numbers, we do have to think about whether those numbers make sense. And in this case, the temperature of a room would never be above 22, 23 degrees, and so we're expecting that kind of value. Okay, we're then asked to say which one is the can painted black. Okay, well, as we said before, that's our line P. Why? Well, because the black can emits radiation at a greater rate, i.e. it cools down faster than, again, I've said shiny here, I mean white can. Okay, so the idea here is one mark for identifying P correctly, and then another mark for identifying a reason for that. Now, unfortunately, if you choose Q here, you will get 0 marks, okay, because you've made the wrong identification. All right. We're then asked about energy again. Okay, the student reheats the water in one of the cans using a heater, and it has a power rating 1.5 kilowatts and switch on for 120 seconds, power and time. Calculate the amount of energy used by the heater. Well, again, we're doing energy equals power times time, and then we're multiplying the power and the time together. Now, there is 3 marks on this question. Why? 1 for working, 1 for the answer, and 1 for a clear statement that we know that 1.5 kilowatts is 1,500 watts. Okay, the answer here is expressed in joules, so you must convert your power into watts as opposed to kilowatts. We then got a question here which is a really interesting one in terms of our understanding of energy conservation. We notice here that we've got energy used by the electric immersion heater. Okay, this is energy used, and we calculated in this value. We're then asked about what the work done is. Well, you should be aware that work done is all about the transfer of energy. And so the energy used is equal to the work done. And so therefore, actually, the 2 values are the same. Now, that is a statement of the conservation of energy. In other words, it's that the energy into the system is equal to the energy out, okay? And the idea that we understand are energy transfers, okay? Again, if we're looking at a point of view where we really don't know the answer to this question, okay, I want you to have a think about the possible answers. If you're stating an amount, it means that there must be an amount on the question somewhere that you can quote, okay? It must be an energy, because we're thinking about work done. Well, there's only really one possible answer here, which is the 180,000 joules that we calculated in the previous question, okay? The only other possible answer may be 0 for some reason. You may think, oh, actually, there's a special condition here, which means that the work was done was 0. So really, you're again narrowing down your options, thinking, okay, it's either going to be equal to my answer here, I've just calculated an energy, or for whatever reason might be 0. Other than that, there's no real answer that could be taken here. Okay, so do take a second. If you're unsure, just have a think, okay, they're asking me what work done, I'm asking to state, I'm not being asked to calculate, I'm asking to state, and so therefore it's got to be something that I could possibly access without doing very much work or any calculations here. Okay, so just be a bit exam savvy, I think, here. All right, make sure that you're thinking about the values that you've written down and what they mean. Last one, and this is one that people like, okay. We're being asked to state 2 ways to increase the rate of evaporation, and we see the 3 here, okay. Increasing the surface area, that means essentially allowing more of my particles to be at the top, and therefore more opportunities to escape. Increasing the temperature, therefore giving more energy, okay. And using airflow, essentially blowing across the surface of the liquid and allowing those top molecules to kind of leave. All right, you only needed 2 of the 3 here, but I thought you could, it would allow you to see the full range of answers there. All right, as usual, have a look, have a think, check your answers, and then move on.